Children, I hope you have gone through my previous video, and today we will continue further. Today in the chapter Hydrocarbons, we are going to study about alkenes. Alkenes are unsaturated hydrocarbons with at least one double bond. They are also known as olefins. General formula of alkenes is CnH2n. You had studied that the general formula of alkanes was CnH2n plus 2. Alkenes is CnH2n. Now next is structure of double bond. Carbon-carbon double bond in alkene consists of one sigma bond, which is very strong bond due to head-on overlapping of sp2 hybridized orbitals, and one weak pi bond obtained by lateral overlapping of 2p orbitals of the two carbon atoms. The alkenes are attacked by electrophilic reagents because pi bond is a weaker bond and acts as a source of electron. Nomenclature: the suffix ene is added to the longest chain of carbon atom having the double bond. Detail of the nomenclature you have studied in the previous chapter. Isomerism of alkenes: they show structural as well as stereoisomerism. In structural isomerism, they show chain isomerism, position isomerism, ring chain isomerism, and in stereoisomerism they show geometrical isomerism. All these types of isomerism again we have discussed in detail in the previous chapter of organic chemistry. Now we come to the general methods of preparation of alkenes. First method is from partial reduction of alkynes. Now in this, the hydrogenation of alkynes with Lindlar's catalyst, that is palladium calcium carbonate poisoned with lead acetate, or partially deactivated palladized charcoal or nickel boride, which is also called as P2 catalyst, gives only cis alkene. So you see RC triple bond Cr plus H2 in presence of Lindlar's catalyst or nickel boride or P2 catalyst, the triple bond gets converted to double bond, and to each carbon one hydrogen atom is attached. Now see the type of attachment. The alkyl groups are on the same side, that is the distance between them is less, and hydrogen are also close to one another. So this type of attachment is called as cis alkene. In the other, RC triple bond Cr plus hydrogen in presence of sodium or liquid ammonia or lithium aluminium hydride, it gives you RC double bond H, RCH double bond HCr. See, on this side it is alkyl group and hydrogen, and on the other hydrogen and alkyl group. So distance between the two alkyl groups increases, and the distance between the two hydrogen atoms also increases. So this type of alkene, it is called as trans alkene. Okay, now in brief, suppose we take an example of but2ine CH3C triple bond CCH3. This on reduction, if the reduction is with Lindlar's catalyst, it will give you cis but2ene. See, CH3 they are close to one another in this case. But if you reduce it in presence of sodium or liquid ammonia at 196 Kelvin, you will get trans but2ene. So the methyl groups, the distance between them is greater. So see, they are at the opposite end. Same way hydrogen atom is also at the opposite end. So this type of but2ene is trans but2ene. Next method of preparation is from dehalogenation of vicinal dihalides. Now vicinal dihalides, they have two halogen atoms. So when you treat vicinal dihalide with zinc in presence of methyl alcohol and heat it, the two halogen atoms, they are removed, and you get alkene and plus ZnX2. So zinc attaches to the two halogens. So example you can see over here, CH2Br, CH2Br. This is 1,2 dibromomethane plus zinc in presence of methyl alcohol and heating gives you CH2 double bond CH2, that is ethene plus ZnBr2. Gem dihalides also give alkenes under conditions. Example, CH3, CH2, CHBr2. This is 1,1-dibromopropane plus zinc. In presence of methyl alcohol and heat, it gives you CH3, CH double bond CH2. That is propene plus ZnBr2. Okay, so this is the second method of preparation of alkenes. Third method is from alkyl halides. Alkyl halides undergo beta elimination and form alkenes by dehydrohalogenation. Hydrohalogenation means that they don't just lose the halogen atom, but they also lose one hydrogen atom. So hydrogen as well as halogen is being removed. So like see here, CH3 CH2Br plus alcoholic KOH. So in this, from this carbon, bromine will be removed, and from the first carbon, hydrogen atom will be removed. So you will get CH2 double bond CH2 plus KBr plus H2O. So since you are losing both hydrogen as well as halogen, this reaction is called as dehydrohalogenation. For a given alkyl group, the ease of dehydrohalogenation is iodides is greater than bromide, which is greater than chloride. And for a given halogen atom, ease of dehydrohalogenation is tertiary, which is greater than secondary, and which is greater than primary. Next is Seitzeff's rule. According to Seitzeff's rule, highly substituted alkene predominates due to its greater stability. Highly substituted alkene means alkene which has lesser number of hydrogen atoms on the carbon-carbon double bond. Like for example, CH3, CH2, CHBr, CH3. In presence of alcoholic KOH and on heating, it gives you two products, CH2, CH double bond, CH2, CH double bond, again it has disappeared, just a minute, that slide has, yeah, this is the slide, no, where did it go? Yeah, this is the Seitzeff's rule. So CH3, CH2, CHBr, CH3 in presence of alcoholic KOH and on heating, it gives you two products. First is CH2, CH double bond CH2. This is but-1-ene because first carbon has the double bond. This is produced 20%, whereas the other product CH3, CH double bond CH, CH3. This is but-2-ene because this double bond is between the second and the third carbon, but this is produced 80%. Okay, so this is according to Seitzeff's rule. This but-2-ene will be produced more compared to but-1-ene. Okay, because but-2-ene is highly substituted. Now next method of preparation is from alcohols by acidic dehydration. This is also an example of beta elimination. For example, if we take ethanol CH3CH2OH and treat it with 95% H2SO4 at 440 Kelvin, you will get CH2 double bond CH2, that is ethene plus water. Similarly, if you take propane 2-ol CH3CHOH CH3, this is propane 2-ol. When you treat it with 60% H2SO4 at 373 Kelvin, you get propene CH3CH double bond CH2 plus H2O. If you take tertiary alcohol like 2-methyl propane 2-ol CH3C CH3CH3OH and you treat it with 30% sulfuric acid at 363 Kelvin temperature, you get CH3C CH3 double bond CH2, that is 2-methyl propene plus H2O. So you see, both primary alcohol, secondary alcohol and tertiary alcohol, all three are showing this reaction. Okay, now like alkyl halides, Alcohols also follow Saytzeff's rule, which says that the more highly substituted carbon will be produced more. So see here, suppose you take CH3, CH2, CHOH, CH3 and treat it with concentrated H2SO4 and heat it. So you get, this was 2-butanol. Now you will get CH3, CH2, CH double bond CH2, that is but1ene, plus CH3, CH double bond CH, CH3, but2ene. So but2ene will be produced 20% and but1ene will be produced but2ene will be produced 80% and but1ene will be produced only 20% because but2ene is highly substituted. Okay. Next method of preparation is Kolbe's electrolytic method. Electrolysis of acidified water using platinum electrodes gives hydrogen. So CH2COOK, this is potassium succinate. When it is electrolyzed with water, it gives you CH2 double bond CH2, that is ethene, plus 2CO2 plus 2KOH plus H2. So these are the methods of preparation of alkenes. Next we come to the physical properties of alkenes. First is the first 3 members are gases and the next 14 are liquids, and higher alkenes, they are solids. Alkenes are insoluble in water, they are soluble in non-polar solvents. They show a regular increase in boiling point with increase in size. Every CH2 group which is added increases the boiling point by 20 to 30 Kelvin. Okay, just like in case of alkanes, straight chain alkenes have higher boiling point than isomeric branch chain compounds. Melting point of trans isomer is greater than that of corresponding cis isomer. Cis isomer of an alkene is generally more polar than the corresponding trans isomer because dipole moments of cis isomer is greater than that of corresponding trans isomers. So these were the physical properties. Next we come to chemical properties. In chemical properties, the first reaction that we will study is addition reaction. Now addition reaction takes place in various ways. First is addition of dihydrogen. So alkenes, when hydrogen is added to them, they give alkanes. So CH2 double bond CH2 plus H2 in presence of platinum or palladium or nickel as catalyst, they will give you ethane, CH3 CH3. Similarly, propene, CH3 CH2 plus hydrogen, it will give you CH3 CH2 CH3 propane. So there you get the corresponding alkane from it. Next is addition of halogens. Halogens like bromine or chlorine add up to the alkene to form vicinal dihalides. But iodine does not show addition reaction under normal condition. The reddish orange color of bromine solution in CCl4 is discharged when bromine adds up to an alkene. This reaction is used as a test for unsaturation. Okay, see CH2 double bond CH2, when bromine is added to it in presence of carbon tetrachloride, it gives you CH2Br, CH2Br, 1,2 dry bromo ethane. Propene also CH3 CH double bond CH2 plus Cl2, it will give you CH3 CHCl CH2 Cl, 1,2 dichloropropane. Next is addition of halogen halides. The order of reactivity of halogen halide is hydrogen iodide is most reactive, then hydrogen bromide, and then least reactive is hydrogen chloride. So CH2 plus HBr gives you CH3 CH2Br. Now the addition of halogen halides to alkenes is done by following Markovnikov's rule. Now what is Markovnikov's rule? It says that addition of HBr or H2O to unsymmetrical alkenes takes place in such a way that the negative part of the adding molecule gets attached to that carbon which has lesser number of hydrogen atoms. Like see over here, we take propene, CH3, CH double bond CH2 plus HBr. Now the negative part is Br. So Br will get attached to CH because here only one hydrogen is there, whereas CH2 has two hydrogen. So negative part will attach to this carbon and the positive part will get attached to the other. So you will get CH3, CHBr, CH3, 2-bromopropane. So this is called as Markovnikov's rule. Now there is anti-Markovnikov's addition also takes place. It is called also known as peroxide effect or Kharash effect. So in this, in the presence of peroxide, addition of HBr to unsymmetrical alkene takes place in the opposite of Markovnikov's rule. But this happens only with HBr, not with HCl or HI, because it follows free radical addition reaction. See here, CH3, CH double bond CH2 plus HBr in presence of peroxide. Only in presence of peroxide. Now, in this case, Br will get attached to CH2 and H will get attached to CH. So, you will get CH3, CH2, CH2, Br, 1-bromopropane. Whereas, in case of Markovnikov's rules, you were getting 2-bromopropane. So, this is the addition according to Markovnikov's and anti-Markovnikov's rule. Anti-Markovnikov's rule is also called as Kharash effect. Next property is addition of sulfuric acid. It takes place according to Markovnikov's rule. CH2 double bond CH2 plus H2SO4. It gives you CH3 CH2 OSO2 OH. Okay, so this is called as ethyl hydrogen sulfate. Similarly, if you treat H2SO4 with propene, CH3CH double bond CH2 plus H2SO4, it will give you CH3CHSO3S CH3. Okay. Next is addition of water. CH3CH. Suppose you take 2-methyl propene, CH3C CH3 double bond CH2 plus water. So you will get CH3C CH3 and the negative part will go to this carbon and the positive part will come to CH2. So you will get OH will get attached to carbon C over here and CH2 will become CH3. So what do you get as the product? 2-methyl propane 2-ol. Alright. So water also is following Markovnikov's rule. And next is oxidation. First type of oxidation with aqueous KMNO4. Now alkenes on addition with cold dilute aqueous KMNO4, which is also called as the Bayer's reagent, produce vicinal glycols. The decolorization of KMNO4 solution takes place. This is used as a test for unsaturation, to test whether there is a double bond or triple bond present. This test is carried out. Now in this, what happens? 2KMNO4 plus H2O gives you 2MnO2 plus 2KOH plus 3 nascent oxygen. Now this nascent oxygen is used for oxidation. CH2 double bond CH2 plus H2O plus O at 273 Kelvin in presence of dilute KMNO4 gives you CH2OH, CH2OS. This is ethane 1,2-diol, which is also called as glycol. Same way propene, CH3CH double bond CH2 plus H2O plus nascent oxygen in presence of dilute KMNO4 at 273 Kelvin gives you CH3, CHOH, CH2OH. Propane 1,2-diol. So this is the oxidation reaction in presence of aqueous, cold and dilute KMNO4. Next is oxidation in presence of acidic KMNO4 or acidic K2Cr2O7 or hot KMnO4. Now the terminal alkenes, that is double bond at the end of carbon chain, are oxidized by hot KMnO4. One of the product is always methanoic acid, which is further oxidized to carbon dioxide and water. So CH2 double bond CH2 plus 4 nascent oxygen in presence of hot KMnO4 give you 2 HCOOH formic acid, which again under oxidation, when it undergoes oxidation with 2 nascent oxygen, gives you 2 CO2 plus 2 H2O. Similarly, CH3CH2 propene plus 4O in presence of hot KMnO4 give you CH3COOH plus HCOOH, which again undergo oxidation to give you CO2 plus H2O. So this is those alkenes which have terminal double bond. Okay, now the non-terminal alkenes which have double bond in the center, not at the corners, they undergo oxidation to give carboxylic acids or ketones depending upon the nature of alkene. For example, see here, CH3CH double bond CH CH3. Now in here the double bond is between the second and third, not for the first carbon. So this is but2ene. This on oxidation in presence of hot KMnO4 will give you 2 CH3COOH, ethanoic acid. Similarly, CH3CH2 plus 3 oxygen in presence of hot KMnO4 gives you CH3 double bond O plus HCOOH. So this on oxidation will give you CO2 plus H2O. Okay, so here ketone is formed. Next reaction is, property of alkenes is ozonolysis. So ethene molecule reacts with ozone to form ethene ozonide. CH2 plus O3 gives you CH2O. This is ethene ozonide, which in presence of zinc and water gives you methanol, 2HCHO. Similarly, propene CH3CH2 reacts with ozone to give you CH3CHO. Again ozonide. This complex which has got 3, which is in which carbon atoms are linked with 3 oxygen, that is called as ozonide complex, which again reacts with zinc and water to give you ethanol and methanol, CH3CHO plus HCHO. So this is ozonolysis, because this ozonide which is formed, it breaks down into ethanol and methanol. Next is polymerization. Simple molecules which are called monomers, they undergo combination in presence of high temperature, high pressure, in presence of a catalyst by a process which is called polymerization to form large molecules which are called polymers, like NCH2 double bond CH2 at high temperature or pressure and in presence of catalyst gives you CH2CH2N. This is polythene. Similarly, propene CH3CH double bond CH2. N molecules of propene at high temperature pressure in presence of catalyst give you CH3CH2N. This is known as polypropylene. These polymers, they are used for manufacture of plastic bags, squeeze bottles, refrigerator dishes, toys, pipes, TV cabinets, etc. Polypropylene is used for manufacture of milk crates, plastic buckets, etc. So this is about alkenes. In our next video, we'll study about alkynes. Okay, revise this.